Okay, how's everybody doing? Let's see. All right, so this is STAT645, biostatistics. I'm going to go through the syllabus today, give an overview of what the class is going to be about, and then we'll get started. So let me go to the syllabus. Syllabus is on eCampus. So let's see, background. My name is Alan Dabney. I'm an associate professor here in the Department of Statistics. I got a PhD in biostatistics in 2006 from the University of Washington, and then I've been here since. My office is just down the hall. So if you go past the bathrooms and keep going to Suite 459, there's several offices in there, and I'm 459B. I'm pretty flexible on office hours. I don't have any specific times written down, usually because people just come by whenever they have questions. So you're free to come by whenever you have questions. If my door is closed, sometimes I keep it closed to keep noise down. Feel free to knock if the door is closed. So the class will be all about the analysis of data from biological applications. That does not necessarily mean high-dimensional biological applications. So some of you may have interests in like genomic data, high-dimensional thousands and thousands of features that you want to investigate. I teach another class in the spring on bioinformatics, statistical bioinformatics. It's 646. So if you are dealing with high-dimensional biological or genomic data, you might consider taking 646 in addition to this class. This class will be more core statistical concepts. In particular, we'll emphasize regression as a way to do statistical modeling. 646 will build on this and expand the applications to the genomic sequencing type data, gene expression data, proteomics data. We're going to use R throughout this class. So R is a statistical software that's free and open source. I'll show you how to get it in just a moment. If you have not had any programming experience, then you will be challenged because we are going to use R, and some R programming will be required. R does everything a point-and-click software program would do for you, so basic statistical tasks like t-tests and linear regression and making scatter plots and box plots. Pretty much any software can do that for you. I'll be giving you examples in script files, so we're going to be making text files in which we write code that R will need in order to do an analysis. You're going to write your R commands in a text file and call that a script. If you have a script, like here's data set X, and I'm going to load in the data, and I'm going to make some pictures, I'm going to do an analysis, and save the output maybe. You would put that all in a text file and then share it with me or the TA or your collaborator, and they could reproduce your analysis. So scripts are a good technique to use. It enables reproducibility of what you've done. So you will have examples, lots of examples, of everything that you have to, every task that I ask you to do in R, you will have at least one example in a script that I give you. So on eCampus, under scripts, all of these are script files, text files. If you download them, you can open them in a text editor. If your computer says, I don't know what a .r extension is, you could tell it, open it in a text editor. So all of these contain R code for specific data sets. Not all, most of them do. There's a couple that are not data specific. So scripts are right here, and I have a separate folder for our data sets. Inside data, these are all data sets that we'll see throughout the course of the semester. Let's see. Back to the syllabus. A couple of specialization areas that we'll cover in this class are correlated data. So if you've had an introductory statistics class, most of what you've seen is applicable to cases where your data were obtained completely randomly from a population. You have maybe in mind the population of all middle-aged women in the US. You'd like to make inference about some characteristic of that population, like the prevalence of breast cancer or something. In practice, we can't usually characterize the entire population because it's too big, it's too cost prohibitive, or maybe it's not even possible. So what we do in statistics instead is take a random sample from the population. If there's so many million middle-aged women at risk for breast cancer in the US, we could list out all their names and randomly pick 1,000 of them, or however many we can afford. That's our sample, and we use the sample, we explore and analyze the sample in order to make inferences back to the population. So usually that data, the sample, is viewed like it's, suppose in the context of the middle-aged woman and breast cancer example, suppose we get a sample of 1,000 middle-aged women from the US. Most of what you originally learn in statistics is geared around the assumption that those 1,000 people are all independent of each other. It's not like you got, here's a household with 3 middle-aged women in it, let's sample all 3 of them. And here's another household with 2 women in it, let's sample those 2. When you sample in chunks like that, what has happened is that the 3 women who came from the same household are related in some way. They share characteristics. They're not independent of one another. In particular, if there's some kind of risk factor that's specific to location, then if this woman who's in this household has cancer, the other 2 who are also in that household have maybe a higher risk of cancer than otherwise. When we take observations from the population in such a way that there's relatedness between them, whether that's 3 women from the same household or 10 measurements on the same person, 1 every 6 months, or 3 measurements of cattle in a breeding program, 1 from the shoulder, 1 from the back, 1 from the chest maybe. These are all cases where there's going to be a correlation between at least some of the observations in our data. And this happens often. This is something you often will want to specifically design for. If the scientific question is about how does something change over time, for example. The women with breast cancer, maybe we give them a treatment, and then we observe them every 6 months and measure some variable like cancer cell count or something like that. Then we might be interested in looking at the time course. What happens after you're diagnosed with breast cancer? Then you're treated with the magic pill, and then we follow you for 5 years, talk to you every 6 months. You have in mind a curve for each individual. That's correlated data. You could also have correlated data from measurements that are spatially located with respect to each other. So suppose you're doing environmental research or forestry research where you're taking measurements on, say, plant life on the side of a mountain. Well, if you take a measurement of some measurement of a plant that's located right here, and then you take a measurement of the plant that's located 2 feet away from that plant, those two measurements are probably going to be more like each other than as compared to a plant that's on the other side of the mountain. The closer you are spatially, probably, the more correlated you're going to be than farther away. Same thing with time. If you have measurements over time, the closer you are in time, take my blood pressure right now, take my blood pressure in 30 seconds, that's going to be pretty closely correlated as compared to now and 2 years from now. So we will spend a couple of weeks on correlated data analysis. Regression is a very general modeling technique for statistical analysis, and we're going to spend a good bit of time on regression. And then when we get to correlated data, we're going to learn how to do regression with correlated data. Most everything in statistics is regression of one flavor or another. We'll see that in the course of the class. So if we can do regression and handle correlated data somehow, then we have a whole toolkit of things we can do with longitudinal data, spatial data, paired data, all kinds of correlated data. Similarly, another type of application that arises in biological applications often is the case where the number that you're trying to measure for each person, let's say we're still with the breast cancer example, maybe what we want to measure is survival time. So from the time that you are treated for your stage 4 breast cancer, say, how many years do we estimate you will live on average? What's the average survival time for women with stage 4 breast cancer under this particular treatment? Suppose you have those 1,000 women in your sample. You could follow all those women, and woman 1, we check her every 6 months, and after 5.5 years, she dies. So the response value for that woman would be 5.5 years, or we might do it in months. Let's say the second woman, we follow her every 6 months, and after 2 years, she moves to Minneapolis or something, and she drops out of our study. We don't have access to her anymore. So for that woman, what do we want to put in the spreadsheet as her survival time? She lived two years, but then dropped out of the study. So should I say she died in 2 years? Should I say, I don't know when she died, so let's throw her away? Or can we do something somewhere in between? So survival analysis is trying to do statistical inference when some of your observations have this characteristic, where you know, for example, this woman lived at least 2 years, but you don't know the exact survival time. So there are regression techniques that are applicable to data like this as well, survival analysis type data. This is a very widely used kind of analysis in biostatistics because you're often interested in survival time. How long does it take for a person to die or cancer to relapse or whatever. And then we'll also spend a little time talking about missing data. So if you have had your own data, maybe you were responsible for actually collecting the data. Or maybe somebody just gave you a spreadsheet that they want you to look into. Often, you will see, here's my Excel spreadsheet with rows corresponding to individuals, people, rabbits, mice, whatever we're studying, and columns corresponding to variables that we measure for each individual. If it was the women, it might be age and race and education level and stuff like that. So often, when you have that spreadsheet, one or more of the cells is missing. It's unknown. So woman 12, we measure her every 6 years, and the last 6-month visit that she was supposed to come to, she couldn't make it. So her row of the spreadsheet has numbers, 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 and we don't have a number. But then she came back and we had more numbers. That's missing data. I can't, and it throws a monkey wrench in the analysis. we have to decide what to do about missing values. It's a very prevalent problem. It turns out it's kind of a hard problem to deal with, and the stakes can be pretty high. If you don't handle missing data carefully, it can really mess up and bias the conclusions you come to. All right. Prerequisites, I'm expecting these prerequisites, the STAT651, 652, are pretty loose. I would like you to know what confidence intervals are, hypothesis tests are, and linear regression. If you know, and I mean know, those things, like could you tell me what a p-value is? Could you tell me what a confidence interval is? How would you interpret a confidence interval and a p-value? What do they mean? And familiarization with linear regression. That's the kind of core stuff you would see in 1 or 2 intro stat classes. If those concepts are completely foreign to you, I recommend that you get a basic statistics book. This 651 has a book that's recommended. It was written by one of our associate head of this department. It's a good book. So if you're rusty on the basic statistics, I recommend get yourself a statistics book and look up those core ideas that I just mentioned: confidence intervals, hypothesis tests, linear regression. In addition to our live meeting times, there's 30 or so students who are following along online. So the microphone is to be recording my voice during the lectures, and also the screen is being recorded, including anything I write on the screen. So if you can't make a lecture, or if there was something that I talked about that you didn't quite get, you can, at the end of the, usually the same day of the lecture, a lecture video will be posted on eCampus. So right here, class videos, there's nothing there yet, but we will have a video for every single meeting session. The primary reason for that is to give the distant students the same experience that you're having. On the syllabus, I mentioned a question and answer session, Q&A session that happens every Tuesday at 7 o'clock down the hall on this floor, blocker 411. What this is like a virtual office hour that, for the most part, is for the distance folks. So this is their opportunity to log in live with me, ask questions, and I can answer writing on the screen and everything. So it's like a virtual office hour. That said, anybody's welcome to come. Yabu is our TA. Can you mind raising your hand? There's Yabu. Okay. He's our TA. He has a lot of grading duties this semester, so he does not have office hours. I have office hours. I'm very flexible. And if you have questions that have not been answered and you are available, you can come to the Q&A and treat that like an office hour as well. By the way, all of your homeworks, let's see, distant students will submit their homeworks through WebAssign. Local students, I want you to email your homework assignments to Yabu and use this dedicated email address in the syllabus, please. So the Yabu's Gmail account. Email your homework submissions to him. Here's the learning outcomes. I've pretty much talked through this already. I'll mention it a little bit more when we get to the schedule as well. Course materials, there's no required textbook, but I do have a couple of books that would be good to get. They're recommended, I would say. So the first is Regression Methods in Biostatistics. That will have some specific content on correlated data and survival data and missing data. So those kind of specialty areas that I mentioned that we'll be covering have content in this book. Applied Longitudinal Analysis is a good readable book on correlated data that are correlated because you measure them over time. So every person in my study gets measured once every 6 months maybe for 5 years. That's longitudinal data. Longitudinal data is ideal for studying and doing inference on changes over time courses. And then applied survival analysis is for survival data. R, you can download, if you just Google R, or you can go to this site right here. So let's go show you what it looks like. Here's the main site for R, and front and center are links for downloading. Okay, so whatever your operating system is, follow the links, get it installed, and then once you open it up, I'll show you what it looks like. This is what basic R looks like. So it is something that you type commands into, like let's create a variable named x that is the numbers 1 through 5. Okay, so here's a variable in R. Why is it doing that? I don't know what happened.
Switch the main screen. Switch the main screen. That one's off.
Yeah, that's good. Thanks. All right, so this is what R looks like, and you will get plenty of practice playing with it. That said, this is not an R class. I'm not expecting you to become R gurus, but R is a full-featured statistical software package. So I would rather you put in the time to learn this software than to just use a an overly simplistic point-and-click software. Point-and-click. Oh, the sharing stopped? Yeah. Okay. Okay. Let me go back to the syllabus here. So I would like you to go ahead and download R onto your computer today. I'll be putting up a homework assignment in the next couple of days. We will generally have one homework assignment every 2 weeks. Here's how the grades will work. Your homeworks will be 30%, and 2 exams, each of which will be 35%. Please save your homework in PDF format. Please also save it as last name, ideally last name _ first name .pdf. That makes Yabu's job easier. For the exams, I didn't make it clear here, but on the exams, you need to bring your computer with you, your laptop with you. I guess there's laptops in here, but you're going to need R on the exams. Exams will be some open response questions, tell me what a p-value is. But it will also be download dataset such and such from eCampus and do the following analyses. So you need R for the exams. Yes?
Do you allow RStudio in the exam?
Yes. This version of R that I'm showing you right here is just the base R. There's also something called RStudio, and I have nothing wrong. There's nothing wrong with using it. I'm not a big fan, but you might like it. RStudio is R with a little bit nicer, well, I guess you could call it nicer, user interface. Some people like it a lot. I really don't see much value over and above R, but you could download it and check it out. The only thing that's different is what it looks like. Okay. Here's our schedule. We'll start out this week with some R practice and basic exploration of data. So step one, whenever you have a data set, is not go do p-value calculations. Step one is to just look at the data, explore it. Think of yourself like a detective. What patterns are here that are unusual? Are patterns that I would expect to be here there? Are there missing values? Are there outliers? That kind of thing you get initially by exploring the data, making pictures and computing basic summaries like the average and the median and the range and the variance and stuff. I'm also going to show you a couple of fairly sophisticated exploratory techniques: principal component analysis and cluster analysis. We'll see those probably starting Friday or Wednesday. Then we'll move on week 2 to begin talking about statistical inference. Most of what we do in statistics is interested in inference. And what we mean by inference is, think back to the breast cancer example, there's a population of millions of middle-aged women who are at risk for breast cancer. That's who I'm interested in. And the parameter in that population that I wish I knew is average survival time, say, after treatment. What we're stuck with in practice is a sample. Here's 1,000 women randomly selected from the whole population. And with these 1,000 women, I can look at them, I can explore patterns. What I would really like to do, though, is say, well, the average survival time in my 1,000 women was 5.2 years. And then infer, with a stated level of confidence, a statement about the population. You can always say, with these 1,000 women, the average was 5.2 years. But the issue is, the statistical inference issue, is that 1,000 women, while representative of the whole, is not the whole. In particular, if I got 1,000 women and computed an average survival time, here's my number. If you went and got a different 1,000 women from the same exact population, but you randomly selected a different set of 1,000, you'd get a different number. And if somebody else did it, they'd probably get a different number. This idea of sampling from the population results in whatever you compute for your sample is subject to randomness. Because the sample came randomly, anything you compute with the sample, call it a statistic, just a number that you compute on data, is random, which means it has a distribution. And that distribution of the statistic, called a sampling distribution, that's the key to doing statistical inference. If you have a sample, you compute a statistic. If you know or can approximate the sampling probability distribution of that statistic, then you can do confidence intervals and p-values, hypothesis tests and confidence intervals. So there's different flavors of inference. There's a variety of ways that you can do this. If you have taken an intro stat class or two, you have learned what I'm calling classical statistical inference. So t-tests, z-tests, things like that. That's inference from 50 years ago. Or 60, a long time ago. We've been doing that for a long time. Nothing wrong with it, but there are options that sometimes are better than t-tests and z-tests. We're going to start our exploration of inference using a more modern technique for inference called simulation. So what we're going to do is use the computer to, using a trick or two, randomly generate simulated versions of our data. Basically simulating that scenario that I was talking about. If I got 1,000 women and computed the mean survival time, and you got 1,000 women and computed the mean survival time, we're going to simulate that process. Here's one sample of 1,000, here's another one, and for each one of them we compute our statistic. If we treat those, all those statistic values that we computed, we can treat them as if it's a draw, a big sample, from the sampling distribution. And we could do inference. So I'll get there. The claim is that simulation-based inference is a very natural concept. I teach this to our undergraduates as well. And I think it, number one, is easy to do with modern computational tools. It's very easy to understand, I think, is maybe the biggest plus for simulation-based inference. And it's very flexible. T-tests, Z-tests, there's these assumptions that you have to worry about. Do you have a large sample size? Is the population normal? Are the variances equal in the two groups? Those types of things. Simulation-based inference can be a lot more flexible. And yet another flavor of statistical inference is Bayesian inference. May or may not have seen Bayesian inference before. You've probably seen Bayes' theorem. So Bayes' theorem, let me just write something down over here. So Bayes' theorem is a probability result where suppose you have two random variables. X is a variable, and its outcome is random. You don't know the value of X until you randomly pick an individual from the population and measure. Could be survival time for a woman. And suppose we have another random variable, Y. There are probability distributions that apply to random variables. We could call these probability density functions. There's a PDF for X and there's a PDF for Y. A PDF, if we were to draw, say, here's Y and here's the PDF for Y, areas under this curve correspond to probabilities. So the area under a probability function is the probability that the random variable is between those two numbers. We can also have a joint probability function. So if Fy tells us about probabilities for Y and Fx tells us about X, then Fx comma Y tells us about pairs. If we want to know how do X and Y, what values do they take simultaneously, pairs. That allows for there to be correlation between X and Y. If X is height and Y is weight, for example, there's going to be correlationships between those two variables. So in order to capture the correlationships, we want a joint probability function. When we have a joint probability function, we can define a conditional probability function. The probability that Y takes a particular value given that X takes something else. That's different from the previous one. Fxy is probability that X and Y equal this and that. Fy given X is probability that Y equals something once we already know that X equals a particular value. And Bayes' theorem, this result right here, if you recall from STAT101, is joint probability function divided by the marginal of the variable we're conditioning on. Bayes' theorem allows us to do this. Switch the ordering of the conditioning. If originally we were saying probability of y given x, suppose we wanted to talk about x given y. So Bayes' theorem allows us to switch the ordering. And we have this f y given x, fx over fy. Bayes' theorem is all about switching the ordering of conditioning. So who cares? Why is that even an important result? Here's where it gets relevant to us. We're going to be talking in terms like this. We have data, x1, x2, xn. Maybe these are survival times, 2.4, 4.1, and so on. These are, we're going to say, independent of one another, mutually independent, and identically distributed. IID, shorthand for everybody's independent, there's no correlation among these people, and everybody came from the exact same distribution. Let's say that the distribution has mean mu and variance sigma squared. Might be normally distributed, might be something else. But let's just say it has some distribution with a mean and a variance. Okay, so suppose we want to do inference on mu. If this is survival time of women with breast cancer, then our parameter of interest is the average in the population. What's the average survival time in the population? Mu is an unknown quantity. It's a population parameter. So in statistics, we take a sample and we're going to try to estimate with a stated level of confidence that population parameter. Okay, so there's two main ways that we're going to see this happen. Strategies for inference. The first, or one that we will see, is based on what's called likelihoods. So I'm just going to call it maximum likelihood for now. I'll tell you more about this topic when we get to it. What maximum likelihood tries to do is say, let's consider a variety of values for mu, and let's pick as our estimate the value of mu that would make it most likely to see data like ours. So if we have some distribution in mind, we have data, we could vary mu, let it go from -10 up to 10, just vary it all over the place. And for each choice of mu, compute the probability, or we're going to call it the likelihood, of seeing this x1 through xn for each of the possible choices of mu. A sensible way to estimate mu would be to pick the value that makes it most likely to have seen the data we saw. That's called a maximum likelihood estimate, and there's a whole toolbox of inference that comes with that. We will see that stuff in week 3, classical statistical inference. Week 4, we will make use of Bayes. So Bayesian inference is a different strategy. It's a different idea. Instead of treating our data, instead of trying to find the parameter that is most like our data, that would make it most likely to be the truth giving rise to our data, that's like an inductive argument. Frequentist statistical inference, which is what maximum likelihood is analogous to inductive reasoning. We say, I'm going to consider a variety of probability models, and I'm going to pick the one that would be most consistent with what I actually observed. Bayesian inference we end up with what's called a posterior distribution. It's a probability distribution where we have switched the ordering of conditioning. A likelihood will be the probability of x1 through xn given a particular value of mu. We would consider that for a range of mu values and pick the mu that makes it biggest. That's analogous to inductive reasoning. Bayesian inference, we apply Bayes' theorem and we get out an actual probability function for the parameter of interest called a posterior. And then if you want to know, given your data, given the data we observed, where do we think mu is? We could take this probability function, draw a picture of it. Mu is varying all over the place. And we could, for example, take the posterior mean, the mean of that posterior distribution as our estimate. So if that didn't click perfectly just yet, don't worry about it. We're going to spend a week on each of these topics, maximum likelihood and Bayesian statistics. But I'm trying to give you a preview. There's different ways of doing statistical inference. Bayesian statistics is very flexible. And if you can figure out how to implement it on your computer, that's usually the most challenging part. Bayesian inference often is computationally intensive. But the good news is that it's so flexible that you can apply it to most any kind of problem. So I do want us to focus on Bayesian stuff. I think it's worth spending our time on it. All right, so we will talk a lot about statistical inference. Then we'll go to regression. And I'll start from the basics, simple linear regression. But then we will move to multiple regression and what's called generalized linear models. Generalized linear models are, generalized linear models are just like regression, except where the variable that you're interested in, the response variable, is not a continuous number necessarily. For example, maybe you've heard of logistic regression, where your response is not like survival time, a continuous number, but it's 1 or 0, dead or alive, say. So suppose you wanted to do inference. What's the effect of this drug on survival, not survival time, but just survival? Let's say 10-year survival. Each person in my data set, they either live or do not live 10 years. So for each person, my response variable is either a 0 or a 1. Can we do a regression-like analysis on zeros and ones modeled in terms of treatment, race, gender, and all of these other covariates that we're interested in? So regression, and then we'll move to correlated data and see how to do correlated data regression, then to survival analysis, and we'll see a couple of techniques for regression with survival analysis, missing data, and then I'll finish up by saying some things about data production. So where does data come from is a very important consideration for the analyst. Is it an observational study, for example, or is it a randomized experiment, a controlled experiment? Depending on the answer to that, the amount of weight or credence that I give to a claim will differ quite a bit. I don't believe all that much about an observational study, but you're going to tend to believe a randomized clinical trial at a higher level, So I'll say a little bit about that. Strength of evidence, how strongly should you believe a claim based on how the data was collected. All right. Are there any questions so far? Okay. So we've got 5 minutes. Let me introduce you to a data set. So under data, I'm going to download these data, weight, height, way down at the bottom. And I'm going to go get a script that goes with that data set. So I was just under the data folder. That's where all the like CSV files are that contain the raw data. Under scripts will be .r files. So let me open one of these up and show you what they look like. Why does it do that? All right, I'm just opening up the data file. It's an Excel file. It's actually a .csv file. I think all of our data sets this semester will be .csv files. That's comma delimited text. You can open it in Excel, and it's also easy to get into R. Here's what the data look like. We have height and weight for each of a bunch of people. How many people do we have here? We have 241 people, I guess, or 240. We have height and weight. We have gender, 0 or 1. I think it's coded zeros for males. No, it's probably zeros for females, ones for males. Race, I can't remember the coding, but we have 1, 0, 1, or 2, or 3. That'll correspond to Caucasian, African American, Asian, or other, I think. But this is just data. Excel spreadsheet, rows corresponding to individuals, columns corresponding to variables. Let me open up the script file. And this is what an R script looks like. So what we will do is go to R, and I'll show you next time. When we're in R, we need to change the what's called the working directory. When you open R, it is opening from a particular location on your computer. Mine currently is pointing at C Windows System 32. So if I were to say read.csv, the weight height data, right now, it would complain because that file is not located in that folder. So what we need to do is change the working directory. On a Windows machine, you go to File, Change Directory. On a Mac, you go to Miscellaneous, Change Directory. But inside here, you just navigate to the right place. And this one's not going to work. Yeah, there we go. Okay. So I'm in the data folder now. The working directory is now the right one. Now I'm going to read in the data. And I think all of our data sets, you can use this command, read.csv. Once you do this, what this command did was read in the file to memory and then assign it to a variable called weight height data. So now we have what's called a data frame, which is like a matrix with bells and whistles to R. What are the dimensions of the data set? 240 by 5. That means there's 240 rows and 5 columns. If I wanted to look at, just take a peek at the very start of this file, if I typed weight, height, data, and just hit enter, it would print the whole thing. So if you have a big data set, you don't want to just print it because it'll be scrolling. There's a command called head that just shows the first 6 rows of a data set. So it's an easy way to take a peek. And there's a function called summary. And what that does is for each of the columns, it gives you some summary statistics. If it's a categorical variable, it tells you about the frequency with which each of the categories happened. for each of these numerical variables, it gives us some summary statistics, the mean, the median, the minimum, the maximum, and so on. Okay, we are out of time. Before we quit, real quick, in the syllabus, I mention a book, I think. I forgot to mention it. There is a book that I am going to post on eCampus details about, and it is the book that I will recommend that you look into when you're trying to get comfortable with R. There's a book called the R Cookbook. You can access a PDF online and through the library.tamu website, so you don't have to buy it. But I do want you to read the first couple of chapters of that because it'll help you get rolling on R. Okay? We'll see you Wednesday then.